introduction and good afternoon. I'd like to welcome you to this talk about how to recover nutrients from urine and actually what is happening here right now in Durban, eThekwini, in means of reactor operation and optimization. And these are the faces behind the names and the team working on the treatment technologies. Just to start with, for those who have been in the session before lunch, Melinda gave a very good introduction to the overall VUNA project. Just to repeat, the idea of the VUNA project is to promote sanitation by nutrient recovery from source-separated urine. Within this VUNA project, there are three main objectives in three main research areas, which are the socio-economic boundaries, the network management, and the management of decentralized reactors, and at the end, the reactor technology. In the session before, Elizabeth Tilly already covered one part of it, is the economic boundaries of urine collection in this project. And after my talk, my colleague Thomas Hook will give you an idea about the network management. But this talk now focuses on the reactor technology. In the VUNA project, we have three different main parties working together. It's the ERAC in Switzerland, the UKZN in Durban, eThekwini, and the eThekwini municipality, EWS. And within the reactor development, we are working closely together. ERAC in Switzerland started to explore different technologies to extract nutrients from urine, mostly in a lab-based and an in-depth research. And just recently started as well to implement pilot-scale reactors. And now this research is taken out of the lab, and the pilot scales are taken out of the lab in Switzerland into the labs in UKZN here in Durban, where we try to optimize these reactors in the means that we can put them out in the field and try a first application of these systems together with the eThekwini municipality. Last would have been a bit long, but hopefully see you there on Thursday to show you the research sites. Within the VUNA project, we are exploring four different urine treatment technologies. That's the Struvite precipitation, the nitrification, distillation, and electrolysis. In Durban, we're going to implement, operate, and optimize the three ones: the Struvite precipitation, nitrification, and distillation. Therefore, I won't go into detail with the electrolysis. To go into detail for the first three processes, first of all, the Struvite precipitation. Kayuda gave already a good introduction to the Struvite precipitation, and we just heard now what is happening in Ethiopia in regards to Struvite precipitation. The process is very simple. By adding magnesium, it is possible to recover phosphates out of the urine. But with this Struvite reactor, you only mostly recover phosphates out of the stored urine. If you come now to the next technologies, that's the nitrification reactor, which aims to stabilize the urine by nitrifying the ammonia to nitrate. Once we have a nitrified urine, which is stabilized and actually good to store, which doesn't change composition, you can distillate it and actually can obtain a concentrated solution, and water is effluent. And the combination of nitrification and distillation enables us to recover all nutrients out of urine. But just to start with, now I want to give you an idea about what is happening here in Durban in regards of the Struvite reactor operation and optimization. Our research is based on the findings of the STAN project in Nepal. We heard it already before. In Ethiopia, they copied the system as well. The same thing happened here in Durban. So we replicated the STAN reactor in the UKZN laboratories. We only did some minor changes. For example, we swapped the manual steering for an adjustable overhead steering to make it easier. Then we took this system, optimized it, and we now have an automated Struvite reactor here in the UKZN laboratories. The volume of this reactor is about 50 liters, and the automation means that the filling, the addition, and the filtration happens automatically. The operator finally only needs to come and change the filters after finishing this process. During the Struvite precipitation reaction, we are monitoring the electrical connectivity and turbidity online. This reactor has been commissioned and started just recently, like 1.5 to 2 weeks ago, more or less. So I can't tell you at the moment the treatment capacity, but we're working on it to see how much is actually possible to treat with this reactor setup. We're using different magnesium sources. So far, mostly magnesium chloride, as it's the easiest to use. But we're exploring magnesium sulfide, magnesium oxide, and as well metallic magnesium. For example, metallic magnesium we obtain out of a sacrificial anode, which is normally used for water boilers. To give an idea how the interface looks like with the reactor, that's the software interface, the reactor control. And with this we are able to operate the reactor remotely and completely automated. And now I would like to do with you a dry run of this reactor. So the operator comes, needs to put in some certain values, for example, the reactor volume, the overdosage you want to obtain, phosphate concentration, and so on. Once he put in all the needed values, can start the process. The filling of the reactor starts, it stops until it's reached a certain level. Then the overhead stirrer starts, and the dosing of the magnesium is started as well. And these dots now in the urine, and the gray one and the brown one just represent ammonia and phosphate, and the black one is magnesium. And now the magic happens, and it's all converted to Struvite. And after finishing the dosing, so we now dosed enough magnesium chloride that we recover all or precipitate all phosphates, dissolved phosphate in urine. We have a certain delay time till we do filtration, that we call reaction time. Just this makes sure that all magnesium which has been dosed into the reactor will react with the phosphates in the urine. After this reaction time is finished, the filtration starts. And the overhead stirrer is switched off, level sensor as well. And as you can see down there, the other level sensor is switched on, and one stays switched off. We have the filtration time. That's one cycle, and actually the whole crux about Struvite precipitation and reactors is the filtration. To do the magnesium dosage, to do the precipitation of the Struvite, it's mainly straightforward, but the crux is actually to get the crystals out of the liquid. We are doing this with a cotton fabric filter, which we just bought here locally in Durban. And actually we recovered about 91% of total phosphorus, of the element phosphorus, not the phosphates. And we only overdosed with about 10%. And we were optimistic. Perhaps you can see in the magnesium dosage sections, there's a dosage mode. It's now manual, and we want to reach an automatic dosage mode. And I want to give you some ideas what we are doing there at the moment to actually reach this aim. The idea behind it, or the motivation, is that we don't need to do any phosphates measurements more, and we can we have the exact dosage for each batch. And the idea is that we use either connectivity or turbidity as a signal to find the endpoint of the precipitation, so that the dosage stops when all phosphates has been precipitated out of the liquid. In regards of connectivity, as we do a precipitation reaction, the ion composition changed, and this gives a change of signal. In regards of turbidity, we have urine, we put in the magnesium, Struvite precipitates, so we have crystals in the liquid, and that changes turbidity. And this change in turbidity should give us a nice signal to finally automate this dosage. And the method is basically to find the optimum curve for ideal control of this process. And to give you an idea now, some graphs. This is turbidity versus time. The different graphs show different magnesium addition rates. And to explain the graphs a bit more in detail, in the beginning you have delayed the dosage time. So like in this time nothing happened besides stirring in the reactor. And we've done this to get a baseline, that we have a stable reading before we start dosing. Then the dosing starts. And we have at the end a so-called reaction time. It's just a small nexus on the curve, and there nothing happens. So after finishing the dosing, we just stir a while longer to see what happens with the curve. And this bars in between is the theoretical end of precipitation. This we get with the initial phosphate measurements. We measured anyway before because we wanted to know where would be the theoretical end of the precipitation. And if you look at the different curves, we are thinking that we think like in between here, we're going to find the optimum curve, which gives us the endpoint of the precipitation just by the signal change of turbidity. So far for the Struvite reactor, coming to the next one, the nitrification reactor. As Kai mentioned already in the session before, that the idea of nitrification is basically that we need to stabilize the urine. If we do not stabilize it, we would have a volatilization of ammonia, and it would lead to a loss of nitrogen. And on the other hand, with the nitrification process, we get rid of the smell, which improves the acceptance of the urine. Here you can see a small scale setup. On the left side is the urine bottle with stored urine, in the middle a small reactor, and on the right side the stabilized urine. Some ideas: the stored urine, pH around 9, ammonia concentration 2.2 grams per liter. Once we ran through the nitrification process, we have a stabilized urine with a pH of 6.5, which actually helps to prevent ammonia volatilization, so low pH, and as well 50% has been converted from ammonia to nitrate. So now we have ammonia and nitrate 1-to-1 in the stabilized urine solution. This small scale reactor has been now scaled up to a pilot scale unit with about 140 liters in the basement of Airwork headquarters. And to give you some ideas, the discharge inflow is about 40 liters a day with a nitrification rate about 350 milligrams per liter a day. This reactor so we do honor measurements to check the operation of this reactor with pH, dissolved oxygen, and electrical conductivity. And as well, remote control is possible that we can check the performance of this reactor anyway. For example, now here in Durban, could sit here and check the reactor if it's working properly. And now the most important thing about this reactor is that without adding any chemicals, we are able to nitrify 50% of the ammonia. This system we have now copied, and we have it at the UKZN labs here in Durban. And again, if you're coming on Thursday and technical tours, you will see this in reality. To give you an idea, this reactor we've commissioned and started as well just recently, like about 2 weeks ago, and I want to give you an idea how we started it. In the beginning, on the left and upper left picture, you see Alexandra taking out the cartons, they're called, out of a box and putting into the reactor. The cartons are just small biofilm carriers which are floating around in the reactor, and the bacteria attached to it, and these should improve the performance of the reactor. In the middle you see us standing on the nitrification step of a wastewater treatment plant at Northernworks, and together with our colleague Longisi from the municipality, we took about 40 liters of nitrifying sludge and put it into the reactor. In the lower picture you see Alexandra pouring in 1 liter of urine to start the nitrification, and as well adapt the microorganisms to the new feed source. And then on the right side you see the ready reactor, and hopefully it's performing well in the next weeks and months. Coming to the last one, the distillation reactor. Just shortly to begin with the process overview, so that we have our stored urine from the urine separation toilets. We have it now it's nitrified, and what we want to do is now, for ease of transport, we need to reduce the volume, and this can be done by distillation. And with distillation we obtain a very concentrated solutions, or perhaps later on, once we reach this concentrated solution, we can even would be able to make solids out of this. And distilled water and the vapor, and this is put back into the heat exchanger, which forces the evaporation of the nitrified urine. In our first test run, it was possible to concentrate nitrified urine about 30 times in a duration of 30 hours. So left you see 600 liters nitrified urine, and right after 30 hours, 20 liters. And this is how it looks like now in the Airwork headquarters. It's on the left side, where the urine comes from, separation toilet, not from this toilet, but from storage tanks in the back behind this door. Then a nitrification step, and finally the distillation reactor. To compare these technologies now, we have the Struvite reactor, and the nitrification distillation. Recovery, as mentioned, recovery rates. Struvite reactor is mostly phosphorus, what we can get out of urine, compared to the combined process, where you get all nutrients out of it, and about more than 95% of the nitrogen. The process itself, Struvite, is rather simple in a one-step process compared to nitrification and distillation, which is a more complex process, and it requires 2 steps. Now the advantage of this combined process is that the effluent is only distilled water, compared to Struvite, where we still have nearly the same composition in the effluent which we had in the influent, and this requires further treatment. Comparison of the products, on the left side, about 2 grams per liter is what we get out with the Struvite reactor, and about 20 to 30 grams per liter we are hoping to get out with the nitrification and distillation. Below that you see a composition of this fertilizer. And here on the right side, down right in the corner, you can see even a powder form of the concentrated urine solution. But in the beginning, we just tried to do the distillation step, a concentrated urine solution, and later on, hopefully, we'll be able to even produce a powder out of this. What will happen in the future? First, we want to finalize the automated Struvite reactor. That means the automation of the magnesium dosage. Then soon we're going to install the same evaporation unit in Durban, that we have the full recovery plant here in the UKZN laboratories. Then again, the field site where you're going to go on Thursday if you are taking place in the technical tours, Newlands Marshall. This needs to be further prepared. You see containers standing there. These are shipping containers which are going to be converted into a field lab, into office and a storage place. And in the storage place we're going to actually implement our reactors. And we're going to as well install some UD toilets. So hopefully in the future when people are coming back to visit the site, they can test UD toilets themselves and see how they like it, how they accept it. And at the end, we want to install field reactors hopefully very soon to get first experience how they work remotely. Acknowledgements, it's a huge team behind this whole study, and I want to mention as well eThekwini municipality. We're doing at the moment all the urine collection for us for the reactor trials, and then especially as well the Bill and Melinda Gates Foundation who's funding this whole project. For further information, don't hesitate, look at our homepage, and thanks for your attention.